Hello, and welcome to my lab for. I decided to talk about the effect of pressure on Bernoulli. I used a soda bottle and an air compressor. I blew the air compressor over the straw that was stuck into the soda bottle, and I wanted to see how fast a different pressure, how fast it would take for the cup to drain based off of using different pressures in the air compressor. So I'll start with my theoretical findings about using Bernoulli's equation to see how fast it would drain, and then I'll compare it to the actual findings, what I found in my experiment. All right, so here's my crude drawing of what's gonna happen. We're gonna have the air compressor blowing air over the straw. The straw stuck down into a volume of water that the pressure difference caused by the speed of the air will suck the water up and then will vaporize it. I got this idea from Destin at Smarter Every Day. He does a series of videos about carburetors, and carburetors use this effect to aerosolize gasoline as it goes into the engine. So the way I calculated it was using Bernoulli's equation. First, I found, well, the important assumptions I had the velocity of the air here equal the velocity of the air there. And through my equations, first I found the velocity of the air exiting the nozzle based off of this pressure. Then I found the pressure to be actually the reverse of the pressure based off of the assumptions in Bernoulli's principle, also based off of the assumption that the air would continue in a similar stream across the straw. So after using Bernoulli's equation and doing all those calculations, I found that it should drain a cup of water at 50 psi in 0.28 seconds and at 65 psi 0.25 seconds. And as you'll see, that clearly did not happen. As we see here, there are a lot of problems with this modeling that I have done, because clearly it's taking longer than a quarter second to drain a cup of water. The first of which is using Bernoulli's to approximate the speed here above the stream, or the straw. It's clearly not, air doesn't act like a tube. As the air exits the nozzle, it won't stay in a cylindrical tube, it'll spread out. The next one is the fact that I calculated the pressure here as if the air went to velocity 0 at atmospheric pressure. The air doesn't go to velocity 0 until over here. And probably one of the other big problems with this model is that, like I kind of mentioned it here, a perfect angle airstream at constant pressure. In reality, I wasn't able to hold the nozzle completely still, and that probably caused some problems. If I were to do this again, I'd make a fixture, test fixture, in order to keep my hand steadier, in order to keep the pressure steadier, and in order to keep everything more consistent.